Hello everyone, this is lecture 35 for the electricity and magnetism. In the last lecture we were studying about the time varying fields, and we have derived the magnetic field and the electric field in terms of the time varying potential, the vector potential and the scalar potential. And we have defined our Maxwell's equation into two equations only. That was in terms of the V and A. So we have find these two equations. Now what we need to see is the examples based on them, that what kind of question can be asked. So let's say if V is given, RT is given, means this VRT is 0, and vector potential at any time is given mu naught I naught by 2 pi log CT plus under root CT square minus R square divided by R. So this is given, A is given and V is given, and they ask you to find the E and B. So how you can find? You will just use direct equations. E is nothing but minus dA by dt, and that is, you can see from here we have find this E, and now you know V is 0, it is given in the question, so it will be simply minus dA by dt. So you need to find the differentiation of A only, and A is already given, just to find the differentiation with respect to time, you will get this. So this is your E. Now to find B, you just need to take the curl of A, and it is in the z cap direction, so take the in the cylindrical coordinates r phi z, then del cross A will be equal to minus del A z by del R. So AZ is just simply the coefficient of z component, so that is this. So this will give you this. So this is your B and this is your E. So that's how you can find directly if V and A are given. We just use the equation which we derived. Now there is one more question. This is a very important question. You must see this. Find charge and the current distribution that would give rise to the potential this. So we need to find the, for a particular element, that what is the charge and the current distribution on it, that will give rise to this. V is equal to 0, scalar potential will be 0, and A will be given by this mu naught K by 4C CT minus mod x square mod x and the whole square z cap for mod x less than CT, and it will be 0 for mod x greater than CT. So this is the condition. A is given and V is 0. So we need to find that what is the charge distribution or the current distribution for which this condition is there. So here this K is constant and C is nothing but 1 upon epsilon naught mu naught, that is speed of light. So first let's find the E and B using this A. So we just find it this way. So we'll do the same thing here. So V is given 0, so E is again minus del A by del D. So just find the differentiation with respect to time. So solve this, it will give you 2 CT minus mod x, then it will be C, and direction will be z cap. So this will be your E. Now you can reduce to this, C will cancel out this. So this is your electric field. Now to magnetic field, just find the curl of A. So A is given, so in the Cartesian coordinate you need to find the curl of A. So this is given in the y cap, so means this will curl of A is in the direction of z cap, so curl will came out to be in the y cap direction, so it will be this. And now inside this, when you just differentiate this, so it will be 2 CT minus mod x. So you are differentiating with respect to x, so the mod of x and del x, so this differentiation is given by del mod x by del x is plus minus 1, means for the x greater than 0 this will be x only, so that will give you plus 1. For x less than 0 it will give you minus x, so it will be minus 1. So that's why you can just represent this in the plus minus 1 form. So when it is plus minus 1, so for the plus it will be minus minus become plus, and for the minus it will become minus minus plus and will be minus. So for the x greater than 0, this overall value will came out to be positive, and for the x less than 0 it will be negative. So that's how you can write just B in the plus minus, means B will be in two directions, that can be plus y cap also and minus y cap also. So this is your B and this is your E. Now we have just find these values E and B, and this B is for x greater than 0 it will be positive, and for x less than 0 it is negative. I already told you the reason. Now see, you need to find the divergence of E. So just find it, because you know the relation from the Maxwell relation, del dot E equal to rho by epsilon naught. So divergence of E is 0, that means the charge density is 0, from because this is equal to rho by epsilon, so rho will be 0. And again if you find a divergence of B, this is again came out to be 0. And now let's find the curl of E. So let's find the curl of E. So if we find the curl of E in the Cartesian coordinates, this is simply Ez, and when you find this, this will be equal to minus plus mu naught K by 2 y cap. Now if you find the del B over del D, you know B, and if you find the minus del B over del D, so that will be came out to be equal to this, means this will give you the same value, because this is the Maxwell's relation. You must know that del cross E equal to minus del B over del D, so that this thing must satisfy that condition. So both will give you the same value. So this is your del cross E. Now let's find the del cross B also, because we know what is del cross B according to the Maxwell's relation. Del cross B is equal to mu naught J plus mu naught epsilon del E by del D. So let's find the del cross B separately and find this value separately. So del cross B will be came out to be minus mu naught K by 2. So you can find the curl the same way as we find it here, z cap. Now if we find the mu naught epsilon del E by del D, so just to use the E from here, and find this value. It will be 1 upon c square, mu naught E naught is 1 upon c square, multiply minus mu naught k by 2 c z cap. So if you solve this, it will become equal to minus mu naught k by 2 c z cap. So this is same as del cross b. Now this must be equal to this, but see, del cross b is equal to mu naught j plus this. So there is one more component, that is mu naught j. So that must be 0, only then this will satisfy, because these are coming equal. So mu naught j must be 0. So that's how you find that current density j is also 0, and charge density is 0. So see, this current density is 0, charge density is 0, then why we are getting this potential? Means from where we are getting this potential? So this is potential we are getting because of surface current. So we need to find the surface current now. So how can we find that? So first let's plot this E and B. So you can see this for the x equal to 0, this will give you minus mu naught k by 2. So if we plot with the x, so at x equal to 0, this will give you minus mu naught k ct by 2. But as x increases or x decreases to ct, this will become 0. Means as it is going to the plus ct, this will become 0, and for minus ct it will become 0. So we'll get, we will get 0. So it will be like this. You will get this type of curve. Now if we plot for the b, so b is, we are getting plus and minus value. So for x greater than 0, we will get plus. So for x greater than 0 means at ct, this will become mu naught k by 2c. So this is at x equal to 0. At x equal to 0, this will be mu naught k by 2c ct. Means there are two values at x equal to 0, that is plus minus. So these are the points at plus minus for x equal to 0. But as x is going to the plus side, this will become plus ct. Plus ct, this will give you 0. And for the minus ct, this will give you 0. And but will in the negative side. So you will get this type of curve for this. Now see, this shows that our magnetic field is discontinuous at this point x equal to 0. Now there is discontinuity, and now if we see that there is this surface in the yz plane, and x is, means we can see that b is changing along x direction, means along x direction this is changing. For x greater than 0, this is becoming positive. For x less than 0, it is becoming negative. So b is changing along the x direction. So if we consider a surface, and we will take just a magnetic field downside of this surface and the upper side of this surface, that will be different, because this surface giving you the x equal to 0. So, and we studied at the boundary conditions that b1 parallel minus b2 parallel is equal to mu naught k, where this k is nothing but surface current, means current per unit length. So this will give you this, and we know what is the difference between the magnetic field, upper side and the lower side. So this is the difference. This minus this will give you a difference. So this minus this will give you mu naught kt. So this mu naught capital K must be equal to mu naught kt. So from there we will just compare, and capital K will be came out to be kt. So this is your surface current, which is giving us the vector potential A, where this K is kt z cap. And you know this A is always, means this surface current is always in the direction. So to find the direction of the surface current, we must see that how is the magnetic field changing. So for the upper side, we know it is the plus y cap, means b is in the plus y cap direction for the x greater than 0. So for the plus y cap, you will just use the palm rule, means it's like this. You will just put it like this, and along the surface current, your fingers along the surface current, then the thumb will give you a direction, that is plus y cap. For the lower side, you will just put like this, means like this. So you will get the direction is along this when you put your fingers and your this side to the outward. Then you will get thumb at the direction of minus y cap. So that's how you can find the direction. So that's why we will get this. So k in the direction of the z cap. So k in the direction of z cap. So I hope it is clear to you, this question, because this question is very important. Many questions can be framed from this. So let's see the today's thing, that is we will study about the Gauss transformation. So we derived these two equations in the terms of the A and B. So what is Gauss transformation? So these are the some conditions we apply to simplify these equations. So we are just assuming that at some E and B, we have the vector potential V and the vector potential A and the scalar potential V. And after changing this E and B to E dash B dash, we are getting scalar potential V dash and vector potential A dash. Now we are just assuming that condition, means if we change this to this, that's E and B will remain same, means E equal to E dash and B equal to B dash. So what change we can do in the V and A so that these remain same? So that is we study in the Gauss transformation. So if E dash equal to A, V dash equal to B, then VA will change to V dash A dash. So let's say we just apply some condition that A dash is nothing but A plus alpha, V dash is something V plus beta. So we added something to A and we added something to V. And what the new vector potential, the scalar potential become, that will give you the same E and B. So that is the thing we will study. So we need to find the value of alpha and beta. So first let's take BD B dash equal to B. So B dash is nothing but del cross A dash equal to del cross A. Now put this A dash equal to A plus alpha. So it will give you del cross A plus del cross alpha equal to del cross A. This will cancel out, so del cross A will be 0. Now from here we can say that alpha is some gradient of some scalar. So that scalar we assumed is lambda. That is called the Gauss function. So we will describe all these conditions in terms of the Gauss function. So alpha is del lambda. So we will add the del lambda to the alpha. So in the value of alpha we will get del lambda. So we need to find beta also. To find B, we'll just assume E dash equal to E. So from here, E dash is nothing but minus del V dash minus del A dash by del T equal to E is minus del V minus del A by del T. Substitute the value of V dash, that is V plus beta, and A dash is A plus alpha. This will give you this equal to minus del V minus del A by del T. So this will cancel out. This will cancel out. From here you will get del beta plus del by del T del. Now in place of alpha, we'll write del lambda equal to 0. Now from here, take the del common. So it will give you beta plus del lambda by del T equal to 0. So this must be equal to 0. So beta is nothing but minus del lambda by del T. So now you have beta, you have alpha. So if you subtract, means if you add this term to the V and this del lambda to the A, then what the resultant A dash and V dash you will get, that will give you same E dash and V dash. So this A dash is A plus del lambda, V dash is V minus del lambda. When you change this way your A dash and V dash, then the resulting E and B will remain same, means E and B will not change. So that is the condition we will use. So you must remember this Gauss transformation. They can ask you the direct question based on this. Now we will study about the Coulomb gauge and the Lorentz gauge also. So these are also the conditions which we apply to simplify our equations, means in the magnetostatics also. So we'll get the same equations like we are getting in electrostatics applying these conditions. So let's see how can we find them. So Coulomb gauge condition is nothing but when we say that if del dot A, divergence of A becomes 0, then that condition is called the Coulomb gauge. And second condition is Lorentz gauge. When we say that this whole component equal to 0, means del dot A is equal to minus mu naught epsilon naught del V by del T, then we will call that as Lorentz gauge. So let's use this condition, second one, the Lorentz gauge. Del dot A equal to minus mu naught epsilon naught del V by del T. So substitute this value in here. So the resultant you will get del square V plus, sorry, it will be minus mu naught epsilon naught del square V by del T square equal to minus rho by epsilon. So this will you will get. Now take this V out, then the remaining operator is called the d'Alembert operator. So just take this V outside, then you will get this del means whatever you call it, D operator, let's say D square V equal to minus rho by epsilon naught. So this is called the, this is your operator which will operate on the V. So this operator is called the d'Alembert operator. So you must remember about this, the value of this. So now you are getting the same equation like you have seen the equation in the electrostatics, the Poisson's equation. So this is the same in that way. So that's why we have applied this condition to get a same condition, more similar condition like the electrostatics. Now we can just apply this here also, means this must be equal to 0. Then again you can see that take this A out, then you will get the d'Alembert's operator. So that operator and A will give you minus mu naught J. So you remember the equation of continuity. So this is the equation similar like that. So we are getting the same conditions here also in the time varying field. So this thing we did just to simplify our things. So these conditions are only valid when this condition is valid, when we apply this Lorentz gauge. So the question can be asked like directly that if the Lorentz condition or the Coulomb gauge is applied, then how the equation will change, and if this is given, then find this and this. So that's how you will use them. So only remember that when we apply this condition, only then we are getting these equations. So that is the thing. Now let's study the new topic, that is retarded potential. Now this is a very interesting thing. What is a retarded potential? So from now in this case we will study a non-static source. Means previously we have seen that source is static, means the field or the charge is not changing with time. But now they are moving, means they are not static, they are moving with time. So then how the potential will change at any point P? So see, if any EM wave is coming out of it and you are measuring the potential due to that, then it will take a time from reaching from here to here, and that time will be equal to R by C. If distance is R, then this time will be R by C. So if you are measuring at any present time t, then that field or the potential will be due to a previously, means when that wave that was emerged at R by C time before. So after R by C time, then you are measuring this, so this potential is measuring due to the wave which is emitted at the TR time. So you are measuring the retarded potential, means this potential at present time is nothing but due to a wave which is emerged a little bit time before. So that's why what we are actually measuring is retarded potential. So you can never find the present time. So, okay, the potential at the present time, always you are measuring the retarded potential or the retarded vector potential. So that is the case, is called the retarded potential. It's like at any time the wave is emitting out of it, then initially there is nothing potential at when it is emitting. So after a r by c time it will reach here, and at that time t you are measuring the potential. So that potential is because of that wave which is emitted r by c time before. So that's why we will quote the potential at t time is retarded potential, and retarded potential time is nothing but t minus r by c. So this you are measuring the potential at because of that time. So what was the charge density and the current density at that time, you are measuring presently that potential. So that's why we call that as the retarded potential, because we are measuring that because of the previous conditions. So I hope it is clear to you. So retarded time is t minus r by c, and the potential currently you are measuring, which is retarded potential, that will be equal to 1 upon 4 pi epsilon naught rho r dash tr, means the charge density at tr time, and this is you are measuring presently, and this charge density is at the previous time, and same that this is your current density at the previous time, and you are measuring your vector potential at the present time. So that is why this is the retarded vector potential, this is the retarded scalar potential. So these formulas will remain same, but this is just the current density at before time, and you are measuring this charge density at the before time. So that's how you will measure the vector retarded potential and the scalar vector potential. So I hope it is clear to you. So there is one more thing, means now if you need to find the B and E, electric field and the magnetic field at this point, so you can't directly use the Coulomb's law or the Biot-Savart law, because this time the field is changing with time and things are moving. So that's why here we use this Jeffy-Manco's equations. So this is the generalized result, you must remember. So E at any time t is given by 1 by 4 pi epsilon naught rho r dash tr. So this is also retarded. So everything we are measuring is retarded. So rho r dash tr, so charge density at the previous time, and the rho dash and the j dash. So see, this differentiation we are getting because this is changing with time, and if it is not changing with time, and it is a static case, then this will become 0, this will become 0, and you will get the same thing as you were studied in the Coulomb's law. So that's why this is a generalized equation for E, and similarly you can have the generalized equation for B also. Again here, if you put this j dash equal to 0, means j is not changing with time, you will get the again what you get from the Biot-Savart law. So you must remember these results. If the time varying field there, then you will just use these equations to find the E and B, and A and V you will find from these equations. Let's consider one example based on this. An infinite straight wire. So an infinite straight wire carries the current. IT is given by 0 for t less than equal to 0, but it becomes I0 for t greater than 0. So that is a constant current I0 is turned on abruptly at t equal to 0. Wire is electrically neutral. Find V and A. So wire is electrically neutral, so this V scalar potential will remain 0 with time. It won't change, but we need to find this A. So let's find how to find A. So we know the formula for the vector potential. RT is given by mu naught by 4 pi z cap. So A will always in the direction of the current. So this is your wire, in this current is flowing in the z cap direction, and we need to find the vector potential at any point P, and we just consider any dz element, and we are finding the vector potential due to this. Then we will integrate, and this distance is r. So A will be in the direction of current, we know this. So mu naught by 4 pi z cap I tr r dz. So now time is there. So now see here, if EM wave is emitting from here, and what is the time required to reach from here to here? That will be r divided by c. So if time is less than that time, then the wave is not reaching here, so vector potential will be 0 here when time is less than r by c. So EM wave has not reached that point ART equal to 0 from this point. Now from this point you will see that you need to again, if you consider this distance as some r, different r. So let's say we have this dz element, this distance is r, so time will be r by c. Now if the time is less than, means r by c, then you will get no potential, but it must be greater than r by c. So t for greater than r by c, EM wave has reached at point segment. So if it is greater than r by c, then you can see that for r by c greater than, it must be like from here you need to calculate the time for this distance also, you need to calculate time for this distance also. So that time must remain greater than that time which is required. Or in other way we can say that this distance traveled by the wave from here to here will be c multiplied t time. So that this distance z must be always less than equal to that distance square minus this square. So that must be always less than. If this is greater than that, then this wave is not reaching there, and you will not get any potential at this point due to other part, because it must reach there only then you will get the potential. So this distance square minus this distance square must be always greater than equal to z. So in that time t, so we will get this condition: mod z must be less than equal to under root ct. Ct is the distance because t is the time, so c multiplied t minus r square. So that distance must be greater than equal to mod z. So this is the condition we have applied. So for a particular range we are getting the means for in a particular time, if we see in a particular time t, so this distance is depending, this z is depending on t time. So if we this t is fixed, then this z will be fixed from a particular limit to that limit. So we'll get the potential only because of that limit, not out of that. From the outer region you will get no potential. So if time is increased, if you take this point outside somewhere, so this time will be increased, so this z will also increase. So that's how you will get your potential at that point. So if t is very small, this z will be very small, because means potential at this point will be because of that small length. So to integrate this complete potential, you need to take the limit only from that part. So this limit will be go from z equal to 0 to this. If you just means this is a even function, you can take at 0 to infinity, multiply with 2, and then now from z equal to 0, this point will be up to this length. Means because this z must be less than equal to this. So if it is greater than this, then you will not get any potential at that point. Because of that part, you will get potential up to this part only. So we just take this and solve this. So minus infinity can be changed to 0 to under root ct square minus r square, and this will multiply with 2 I naught by under root z square plus r square dz. So this is your vector potential now. Means this r is fixed, that's why you are getting this, and this time will be fixed with the r. So ART will be given by, now just need to integrate. So this integration will give you log z square plus r square plus z. Now substitute the limit 0 under root ct square minus r square. So the substituting the limit, you will get ART as mu naught I naught 2 pi log ct plus under root ct square minus r square divided by r z cap. So this is your vector potential. I hope it is clear to you, and if you are still having any doubt, just put in the comment section. I will try, or I will put a short video for that part where you are having doubt. So thank you everyone.